Hello APC Mechanics students, today we'll solve the past paper FRQ 2004 exercise number 2. So always remember that the figure appears to be above the exercise. A solid disk of unknown mass and known radius r is used as a pulley in a lab experiment. As shown above, a small block of mass m is attached to a string, at the other end of which is attached to the pulley and wrapped around it several times. The block of mass m is released from rest. This is important, which means the initial speed is 0 and takes a time t to fall a distance t to the floor. Now, in part A, they're telling us to calculate the linear acceleration A of the falling block in terms of the given quantities. We know that A is accessible either from dynamics or from kinematics, basically because they have mentioned the time and the distance. So we can indeed determine the acceleration of the block in terms of the given quantities by utilizing the vertical motion. The equation that we're interested in is given by y is equal to y0 plus vy0t plus half ayt square. Now the initial position taken as the origin and the initial speed is 0, and the final vertical position, which is basically the distance d, and in this case the acceleration, if we're taking the positive direction, is down because y is capital D, then this would be g, which means that d is given by half at square. Then the acceleration would be given by the double of d divided by t square. Now in part B, they're telling us the time t is measured for various heights d, and the data are recorded in the following table. We have in the first column d and in the second column t. In idea number 1, they're asking us what quantities should be graphed in order to best determine the acceleration of the block. Explain your answer. Now, since we have the variables d and t, then one suggestion would be to isolate d as function of t, and this would be given by d is a divided by 2 multiplied by t square, and if d is identified by y and t square is identified by x, then the slope is equal to a over 2. Then we can determine the acceleration by multiplying by 2. So let me say along the horizontal axis, we will plot the time squared which is basically t square, and its unit would be second square, and on the vertical axis we will plot the distance d given in meters. On the grid below, plot the quantities determined in B idea 1, label the axes and draw the best fit line. Now as we have agreed that we're gonna plot d as function of t square, so let me add the following column given by t square and has unit of s square. So let's determine the square of each of the following quantities. Now 0.68 square, that would be 0.46, 1.02 would be 1.04, and that would be 1.42, and 1.38 would be given by 1.904. Now let's start by dividing our vertical axis. As you can see, it's perfectly given by a step of 0.5. So let me say this is the vertical. Now it's convenient to start from the origin. That would be 0.5, 1.0, 1.5, and that would be 2.0. Now the vertical axis represents d in meters, and the horizontal axis would represent t square of unit of second square. Now let's look at the division of the units of the values. It's convenient to divide it by step also of 0.5. So let me say this is 0.5, and that is 1.0, and that would be 1.5, and that would be 2.0. Now starting by the first value, it's given by 0.46 for 0.5. Then if you look carefully, that would be 0.1, 0.2, 0.3, 0.4. So 0.46 is somewhere here for a vertical distance of 0.5. So that's the first point. Now the second point is given by 1.04. So that would be 1.1. This is 1.04 for a vertical distance of 1. So that's the second point. Now the third point is given by 1.42. This is 1.4. 1.42 is somewhere here with a vertical distance of 1.5. And the final point would be 1.904, which is almost 1.9, with a vertical distance of 2. And now we connect these points and try as much as possible, if it's not passing through all the points, to be equidistant. Then let me try. I think that works perfectly. Let me adjust it more. Okay. So that would be our best fit line. Now in idea number 3, they're telling us use your graph to calculate the magnitude of the acceleration. And we know that whenever the graph is a straight line, basically we have to feature slope or area. And whenever we're doing a best fit line, we're mostly interested in the slope. So let's calculate the slope. Now here, let's choose points that are clear for us in which we can pick their coordinates easily. Now the first one, which is basically found here, so 0.5 with 0.5, and the second point, if you look carefully, no, that's good, which is given by basically 1.2 and 1.2. Then now let's start the slope calculation. So let me say slope now would be given by 1.2 minus 0.5, and the unit of the vertical quantity is given by meters, and for the horizontal that would be again 1.2 minus 0.5. now in seconds square, and the slope in this case of our best fit line would be 1 meter per second square. And how we will use the slope in order to determine the acceleration. So first we know that the acceleration determined in the previous part is given by 2d divided by t square, which means that d can be written as a divided by 2 multiplied by t square. And we know that the slope is identified or calculated by 1 meter per second square, which means that a over 2 would be equal to 1. This means that the acceleration is given by 2 meters per second square. Now in part C, they're telling us to calculate the rotational inertia of the pulley in terms of m, r, a, and fundamental constants. Okay, so in order to determine the rotational inertia, whenever you're speaking about rotational inertia, you should think about Newton's law for rotation or energy. So here it's more convenient to think about Newton, because that would be also, we need to apply it for the block in order to determine the tension. So let me say, first let me start by applying Newton's second law for rotation for the pulley, then apply Newton's second law. Now here it's not much important whether we say translation or rotation, but let me identify that we're interested now in the pulley. Which means the torque net is equal to I multiplied by alpha. And what are the different forces that would be acting on the pulley? We have the tension down, we have the pull of gravity, and F at the axle, or at this point at the pivot. So we will say the torque produced by gravity, the torque at the pivot, and the torque due to the tension. These will cancel. That would be I multiplied by alpha Now we don't split I because we're interested in determining I. Now what is the torque produced by the tension? We know that tensions always provide tangential torque, and in this case that would be the tension that we're interested in. Let me say it's capital T multiplied by the radius r, that would be equal to I multiplied by A divided by R, and here we're assuming that alpha is equal to A over R because we need to do that assuming that there is no slipping. Then T multiplied by R square would be equal to I multiplied by alpha. Now in order to determine I in terms of these, okay, we are allowed to express in terms of R and A, but we need to replace T. T can be replaced by applying again a Newton's second law for the block. Then let me write apply Newton's. So here it's better to mention second law. But now we're interested in the block. And in this case we have that F naught is MA, which means the pull of gravity plus the tension, let me say it's capital T, equals to MA. So remember, this is a vector equation. We need to project it. I will project along the vertical, taking the positive direction to be down. Projection along the vertical. Then mg is positive, the tension is negative, that would be equal to ma, and this would directly give us that the tension is equal to mg minus ma, and this is what we expect for the tension when an object is moving down. Now this expression will be replaced here, so we have mg minus ma multiplied by r square is equal to r multiplied by a, and now we can isolate for I. Then I in this case is given by, now we can factor out m and r square, that would be mr square multiplied by g minus a divided by a. So if you check, this is the first time that we get a fractional mass, a fractional acceleration multiplied by mr square. This is a very important result. So indeed we have expressed our answers in terms of m, r and a, and fundamental constants basically, which is g. Now in part D, which is the last part of this exercise, they're telling us the value of the acceleration found in B idea 3 along with the numerical values for the given constants, and your answer to C can be used to determine the rotational inertia of the pulley. The pulley is removed, its support and its rotational inertia is found to be greater than this value. Give one explanation for this discrepancy. So what's happening here is that we have determined our rotational inertia theoretically or experimentally, experimentally. Then we have detached the pulley, and using a certain technique we have determined the rotational inertia, and it's happened that the actual rotational inertia is greater than the one we have determined from our experiment. So one reason or one explanation for this happening is basically we might have measured an acceleration from this distance and this time from the values of time to be greater than the actual, or we have measured an acceleration which is greater due to the reason that we haven't taken into account that the string around this pulley is slipping. So if the string is slipping over the pulley, which means that we're measuring an acceleration, but how this acceleration can be compared to the rotational inertia? Because it's slipping, the inertia of the pulley must decrease this acceleration. So as it slip, we will measure an acceleration, but this acceleration will be greater, which means we didn't take into account, or it's not rotating the pulley because it has inertia, it will decrease the actual value of the acceleration. So in brief, we're measuring a greater acceleration. A greater acceleration, even you can look at this expression, would give us a rotational inertia which is smaller, because if A increases, the numerator will decrease, as well as for the denominator will increase, which will decrease the value of I. So let me say if the string happens to slip over the pulley allowing the block to accelerate faster, resulting in a smaller experimental moment of inertia. And that's it for me in this video, guys. See you soon in a new one.